like what size is considered thin lens? Like how thick? Like you're talking like a contact?
Oh, that definitely would be a thin lens.
Okay, so we're talking like,
No, it doesn't have to be that thin.
okay.
Not that. Oh, there we go. Copies. Yeah, this would probably still be, this would still considered thin lens.
Is that a millimeter? And width?
Oh, that looks pretty thick to me.
Yeah. There, I do. Wait. Yeah, it's probably gonna have a smaller focal length than.
Somebody blind.
Yeah, sort of get some idea right there. Focal length at that distance.
Look like one of them Western glasses with the guy in a Coke bottle with
I
glass.
think I have a magnifying glass just like that, except it's bigger.
Yeah. Sense of thin lens. It's, for what we're doing, yes, we do consider that a thin lens.
What is a thick one?
That's what I was wondering.
Trying to think if we have any thick ones.
Just pull the window off the,
So that's still relatively thin.
wow.
I don't know if we have one. We have larger ones, but that doesn't necessarily make them thick, it just,
What about a magnifying glass, would that be considered a thick lens?
I still consider those thin lenses. So the question is, when you're doing the calculations, how close is close enough? Is it good enough to be close enough, or do you need the actual precise measurements? And for anything I've ever done, it's close enough to a thin lens.
I remember there was a video where a guy took a giant lens in his backyard to burn obsidian back into lava. I think that'd be a thick lens.
I don't know, it could be.
It was like this thick.
Ah, okay. All right, so the geometric approach to it is, again, light that comes in. For a mirror, it would go through the focal point. For a lens, it's going to go through the lens and then go through the focal point. So light that comes in straight will bend, go through the focal point. So if I have an object, let's put the object here, light that goes through the center, just goes through the center. And this is absolutely horrendous drawing here. And then light that goes through the near focal point, when it hits the lens, should go straight out, and those three clearly meet in this single point. I'm gonna try to draw that one again.
Yeah, I got lost real quick.
Oh yeah, we should try.
I was drawing my first line, and look up.
Those are supposed to be perpendicular. This is my axis of symmetry.
Alright.
This is my thin lens. I have a focal point here, and I have another one on the other side at the same point. I have an image, which I'll make smaller this time. So again, it's all about light that's coming off of it that we are seeing, but usually light hits it and bounces off. So light that comes in straight. Remember the absolutely spellbinding tale I told of the cattle ranch? So light that comes in will then go through the focus. So light that comes in off that, because light's going to be coming off this in all directions, presumably. And so light coming off the tip here that comes in straight will then go through the focal point.
Okay.
Light that goes through the center just travels straight. For a mirror, it would bounce back at the exact same angle at which it hit it. It's supposed to be a straight line. And then light that goes through the near focal point is then going to come out straight. And if done properly, all three lines would intersect at the exact same spot. But clearly, I can't draw.
I can't either.
Well, would that go for, I mean, yeah, there's an infinite number of lines right there.
So, once we establish, let me see if I can draw it better, and then I'll talk about the other lines. You've done it perfectly in your notes. We're already, all right, so is that level?
No.
No.
Your left hand up a bit.
I think it's 36.9 the figure.
All right,
There you go.
yep, so,
I think the
well, no.
figure is 36.9.
All right, hold on. All right, I have all the perpendicular there, that's looking perpendicular to me. Let's put the focal point at 10 centimeters. All right, so focal point, so my focal length is 10 centimeters. I can put an image at 15 centimeters, or an object, sorry. And I'm gonna make it, let's give it a height. Five centimeters tall. So the height of the object is 5 centimeters, and the position of the object is 15 centimeters. Light that's coming in straight, that's coming off of this, straight towards the central axis of the lens. It's looking somewhat parallel there. It's gonna hit the lens, and it's gonna get focused towards the focal point. So one light right there. Very similar to the mirror, except for the mirror that the light then bounces off and goes through the focal point. Next step, light that goes through the center will just go through the center. And it's close enough to a straight line. The advantage of the thin assumption. And then light that goes through the near focal point. It's gonna come out better than the last two drawings, not have to be much worse. It's gonna hit there, and then it's gonna come out straight,
Oh, not sure. Yeah.
and I am obviously going to exaggerate this because I want it to get closer to. That last one should be parallel to this line right here. I just was desperate to have some sort of win there without being hit in the same spot. So it's going to appear that the object is here. So if this is a magnifying glass and I'm looking at an ant on the other side, the ant's going to appear bigger and on this side of the lens.
Sorry to interrupt, I just want to turn right in.
Right.
So that's the image through the magnifying glass.
This would be the image. Yes. The image would appear to be closer to you. Your brain would process it as such. Now, the equation which describes all this is the exact same one we use for mirrors. It is designed to sort of think of natural, sort of a natural aspect to it. mirror, when Q is positive, that means that basically positive Q, the light's actually hitting there. So in this particular case, we'd have 1/15 plus 1/Q is equal to 1/10. For lenses, because light goes through the lens, a positive Q means that Q's on the other side. So 1/Q is equal to 1/10 minus 1/15. Q is 30. Because that would be 3/30 minus 2/30.
130.
Okay. And if you just look at this, that's clearly 30 centimeters right there. Spot on. I have done this on graph paper. It does come out really nicely if you take the time and care to do it. Really not a whole lot of success doing it on the board.
And it doesn't matter, like the negative sign doesn't matter.
The negative sign?
Yeah, it says, you put 1/10 minus 1/15.
Right, which would be a positive.
Oh, okay, yeah.
Right.
So how close did you get?
You know, I'm buying the spot on?
No, I just wanna see how close.
Actually closer than it looked, 30, just shy of 32 centimeters. Better than most physics demonstrations. Which probably this one was more accurate than one of these two was off. At least one of them. Now, if we end up with a negative Q, so let's say that we put this thing inside the focal length. So let's put it at 5 centimeters. So put P is equal to 5 centimeters. 1/5 centimeters equals, plus 1/Q is equal to 1/10. 1/Q is equal to 1/10 minus 1/5. And so Q is equal to negative 10 centimeters. Where's the image going to appear?
Farther away.
Which side of the lens?
On the side of
It's,
the
the image.
object.
Yeah. It'll be over here. In that case, and I'm gonna freehand it. We had a focal length of 10 centimeters, and I said put the object here. Light that comes in straight will go through the other focal length, other focal point. Light that goes through the middle will go through the middle. And you can see that because this is inside, these are diverging. But it's again about the brain processing here. Your brain's going to trace these, basically the lines backwards, and it's going to see the image here. Magnification, it's obviously bigger, but the exact same rules apply as did before. Magnification is negative Q over P. So in this case over here, it is negative 10 over 5, or 2. So it should be twice as big as what I started with, obviously drawing off.
So if you're looking at the magnifying glass, the object would appear behind you?
It depends on where you're sticking your eye.
Like, if you are holding or if you are holding the magnifying glass, and that's what the focal point is. if the object that you're looking at appears like 10 centimeters behind you, it would, I don't know how that even look.
So if you were doing the magnifying bit, that means you've taken a magnifying glass with a focal length of 10 centimeters and you basically got the magnifying glass probably too close to really see much detail. The object will be twice as big, it'll look upright, but it will, well, in essence though, I guess the way you described it is your eyeball is right here. That, because normally when you have a magnifying glass, my face is usually not so close to it that I'm within the focal length. That, all right, this is what I'm looking at right here, this is my object, and that's my image. And actually, it's gonna, if I'm over here looking through a magnifying glass, it's gonna look like the image is on the other side. Not on the same side as my eye, but on the other side.
I was more picturing on this
This one right here?
picture up here. Say you were looking at the object, and it's bigger because you're looking through the magnifying glass on that side. But if you were standing on the left side and you're looking at the image, and then you
I'm over here looking at the image?
yeah, you're over there looking at the image becoming bigger.
So I've got the object between me and the lens?
No, you got the lens in between you and the object.
So my eye's over here. This is the object right here, this is the lens. If that's a magnifying glass, I'm over here looking at it.
I'm confused.
So
Because I pictured,
So your Q and P don't, all you use those for is to find the magnification. You know?
Well, I mean, and also what will the image look like? So this is basically, there's my lens right there, I have an object right there that I'm looking at, and, oh, that's a different focal length, but if that's right there, then the image is going to appear, my brain's gonna process it like the image is here.
so the image is, your brain is gonna process the images right next to you.
Yeah, now, throwing something else into that is, if I'm bringing my eye into the system, my eye is so close is that you now have a multiple lens system. And so we'll deal with the multiple lens system, actually probably today, but.
Right. So the object appears right next to you.
Right, okay.
On the other image, on that part, it looks far away, but it's bigger.
Yeah, so, I think, at some point, because if I am, so in this situation right here, I had it within the focal length.
Right.
So if I was doing something like this, you're well past the focal length.
Mm-hmm.
And the image is upside down and smaller. So I need, if I wanna make it bigger, there is sort of an optimum distance there for this particular lens. Yeah, the fry's looking bigger. And somewhere around there, it's roughly the same size. And the image looks like it's on my side of the lens. I figure that's upside, no, it's upside down. Right, express your concern again.
Okay, so say on this image, like you're holding the magnifying glass.
Okay.
The image that you see, the one on the right, looks bigger because it looks closer to you.
It looks bigger. Not necessarily because it's closer to me.
Now, I know it's not literally closer to you, it just appears closer to you.
So the issue you're having is the fact that this image appears farther away and is bigger?
Yes, like it's behind the object. It actually is.
Yeah, the lens. I don't have an issue with the fact that it can appear bigger and be farther away. Trying to think of what we have here that. Interference plate, interference plate. Plain glass. Most of our lenses are small. That's just a glass. Alright, so let's see if I can satisfy it. Let's just make everything smaller. That's not gonna do it. Alright, so let's first figure out what the focal length of this lens is. Alright, ideally, we pick some place that is noticeable far distance away. I'm gonna just use the lights for right now, and I'm basically taking this until I get a focused image. Oh, wait, no, focused image on the
Put a
table.
piece of white paper over, under it.
Well, there's many lights in here.
Yeah, definitely doing the one right above it. That's because of which part of the light I'm doing. Alright, so very crudely, that's the focal length right there. Because that's when the image is looking clear to me. So that's an infinite distance away.